In the last episode, I was explaining what's the relationship between, in this case, it was an SIR model for one population, homogeneous population, but with delay, and the stochastic individual-based models. Now I was concentrating only on one, but you can imagine that, of course, the same is true if you have K subpopulations and you have these individual-based models for the subpopulations. As long as the number of subpopulations is finite and the total rate of infectious is not infectious people is not too small, you have this kind of limiting behavior for several subpopulations, the same as for one homogeneous population. And what you get out of it is the same kind of equation. So it's this partial differential equation, or sometimes we call it an age-structured delayed differential equation, where you have this the rate of change of the susceptibles in the J subpopulation changes by people getting infected, so becoming infectious, maybe not at this time t, but maybe at the time t plus a0, as I was explaining before. And this rate there, this rate at which infections, new infections happen, is proportional to a contact rate between the susceptibles of this J's population with all the other infectious individuals of all the other populations. But there is, of course, a rate, and this is this rate alpha JL. So you have this rate alpha JL, and then you have this integral from the incubation time to the final time of your infection of all the ILTA, where A is the time that since infection for the individual in the ELF subpopulation. And as I was saying, the only way that the individuals get removed before the time d, of course, if this integral goes only up to the time d. So, I mean, after time d, they are removed in any case, but before the time d, the only way they are removed is they are detected. So that happens only, well, let's say by the virus test, so only after A is larger than A0 with a certain probability, and that is this rate delta J, which we have there. As I was already explaining, you can solve such an equation more or less explicitly if you know this ij of t0. So that is what I'm writing down here. And what you get, that's, no, maybe I will, sorry. I know now what I do. And what you get is actually this type of relationship. So that is a relationship which couples the ij at t0, that is 0 is the infected at the time 0, now to the ij of ta, and you use just the equation as an equation in the variable ia, but you have to know, of course, what is the dt of ij of t, right? And that's what I'm writing down here. So you have not only something which depends on ij of t0, but you have also another term, which is an integral with a certain weight, which I don't go into that. You can, I mean, if you know calculus, you can try to do it for yourself. And then multiplying the rate of change in time of the ij of t sigma, and all the sigmas are involved here. Now, that leads finally to another kind of equation, That's what we call it. It leads to integrals. And what do I mean by this? Well, if you want to solve this kind of linear on a differential equation, you separate variables. And you separate variables by dividing by this sj of t and observing that dt sj of t over sj of t is, of course, the time derivative of the logarithm of sj. And this way, you have, this was a kind of a nonlinear relationship because you have this IL of t fida in there. But now it becomes, for this dtsj, a linear relationship in terms of this IL of t and a. And if you go back to this equation here, and you observe that, of course, the ij of t of 0 was nothing else but the dt sj of 0. And you observe that this one here, that the time derivative, I mean, there's no time derivative here. There's no time dependence of this coefficient. So the time derivative can get out. Then you will see that we have a new relationship which says that there is a quantity which stays constant for the J's population, or let's say for all these populations. So it's the logarithm of Sj, as I was explaining, minus. Then you have this kind of modified AJL, alpha JL. This I call the AJL now. They don't depend on anything, right? This is the D and A0, so there's just constant. So it's just the matrix AJL as L. And then, of course, you have something which is basically this part of the identity up there. So it is an integral, a weighted integral, weighted with coefficients in A, of the level of infections in the L's population. Yeah, so that's what you have. And when you look at this, then you see, of course, it is now, well, I mean, the structure is in there, but as mathematicians, we say it is kind of this term which we have here, this BJL ILTA, this integral there, that is like a linear projection. So we have these kind of basically there are curves which we have there, and the space of curves is, of course, a huge space, but we are just looking at one particular weighted integral of this one. Of course, it's not completely true. We are looking at the matrix of weighted integrals of these IL of TA, and that gives us the effective level of total infections in this model that compensates this ln_sj minus ajl_sl. Now the first part here is just a function which depends on s, right? And the second part is a function which depends on on the current level of infections. And what it tells you is all of these coefficients are positive. What it tells you is that this during the course of an infection, also for this fairly complicated model, you know that this kind of function ln_sj minus ajl_sl, that has to somehow, when you start, it has to when you start from 0, right? Then this function has to actually increase, yeah, and finally, of course, it will decrease again because this thing will turn to 0, and the level at which you start with during an epidemic with 0 infections, and the level at which you end again with zero infections is just determined by the zeros of this function, ln(sj) minus AJL(SL). And I will just, in order to make this a little bit clearer, I will explain this on the other blackboard again, so that you can see what is coming out. I'm just was able to erase things and write down a formula that I wanted to write down again. So compare this kind of what we call this set of invariants, which we have for this complicated model, for the time age-structured SIR model for several subpopulations, compare it to the simplest case, the simple SIR model, where I was renormalizing time so that the coefficient beta was equal to 1. So we just have this equation dTs is minus alpha is, and dTi is alpha is minus I. Now, when you see what happens when you do this separation of variables, you get the function here that we have, that is this dt of log s is minus alpha I, and that is, sorry, there was something wrong there. That is dt of I is minus I plus alpha is. So it is dt log s. So sorry, it's plus and plus here, right? Minus alpha I, so it's alpha, yeah. So when we see this, so we have just the one scalar integral or invariant, that is log s minus alpha I minus alpha s. And of course, we know what the shape of this logarithm is. It's a convex function. The other parts are linear. So the function log s minus alpha s, which we have there, has then usually two zeros that we put down, or two levels, which are the same, which give you the same number. At each level for log s minus alpha s, you have two solutions. You have one unstable solution where the function is where the ordinary differential equation which you have here actually gives you an unstable trajectory, which then finally will hit at a stable point s, which is at the same level for this function log s minus alpha s. Now, if you look at the structured SIR model, which I had there, and this is on this, we had something very similar, only that this is, of course, time dependent. It's an integral. It's a delay equation. But if I'm just interested of where does it go to, where does it start from, where does it go to for I equal to 0, doesn't make any difference whether I'm looking at this complicated equation or whether I look just at the simple equation where I have no delay in there, and I have just the corresponding equation for Sj. So I would just have here the corresponding equation, dt Sj. Then you have this AJL, and here you have IL Sj, and here you have dt which I call this dTij, and here I have the same thing, alpha j L, IL Sj minus, and in this case it's minus Ij, right? And you see that this much simpler equation, of course it has the structured subpopulation, will give you asymptotically the same. Of course, the trajectories are not the same by any means, but since everything depends just on the solutions of this kind of function, fj, so it is a function fj of s, and that is just the logarithm sj minus, and here you have just this sum L equal 1 up to k, A j L S L. So since it connects two values S, or vectors of values S, from which have the same value for all these fj's, therefore the asymptotic behavior, where the final what the final outcome of the epidemy is the same for the complicated model and this much easier model, which has the subpopulations but doesn't have any delay in there. And intuitively, this is something which is not so surprising, because at the beginning and at the end of the epidemy, of course, the number of infectious is actually 0. But what is a little bit surprising is, of course, that this, or it's in the end, it's a matter of calculus, that this fj of s has only one stable solution, and this one stable solution is where you are going to. But this is a fact which comes out of the theory of monotone operators in the sense of Krasnodębski. So it is just a mathematical fact that if you just are interested in the final outcome of an epidemy, starting from an unstable set of susceptibilities Sj, then it's not necessary to really look at the age-structured model, or to look at the stochastic model for that matter, but it is just enough to look at this much simpler SIR model with several subpopulations, but no stochasticity and no age structure in there. So thank you for your attention.